3, 2, 1. Alright, another Math 2070 online video. Alright, so as promised in the previous video, today, in this one, we're going to look at some specific subspaces, some of fundamental ones, and then while we're at it, we'll bring back linear transforms. Alright, so for an n by m matrix A, we have access to the following sets. So we'll start off with the null space, which we'll denote as null L. This is the set of solutions to the associated homogeneous equation, ax equals 0. So the system of linear equations where the right-hand side is 0, and the coefficients are given by the entries in the matrix. So, more precisely, this can be written in set notation as follows. I'm missing a pause in our slide. Got too much on the slide, not what I wanted. There we go, beautiful. All right. So, in the precise set builder notation, null of A is a collection of x, so that x is hanging out in Rm, and A times x is equal to 0. All right. Spoilers. Next up, the column space of our matrix A, col of A, is the set of vectors B, so that Ax equals B has a solution. So note the subtle difference here. In the null space, the x we're talking about are solutions. For the column space, we're talking about the things on the right-hand side, so that Ax equals B actually has a solution. So the b's are not the solutions, the b's are the things on the right-hand side so that we do have a solution. So in precise set builder notation, it's the collection of elements of Rn, so note the size of the matrix and the corresponding sizes of the vectors here. Now, this interpretation of the null space is a little clunky, the column space, right? The null space is nice, the set of solutions to the homogeneous system. No more. The column space is a little bit more clunky, the things on the right-hand side, so that you actually have an answer. But recall there's a better way of thinking about this. The column space can also be considered, well, the elements B that can be written as A times X. But recall, A times X is the linear combo of the columns of the matrix. So in other words, the column space is precisely the span of the columns. I don't know what that 0 is doing. Slide 1, we already got goofy stuff happening here. Alright, so, in other words, a better way of thinking of the column space, hence its name, is that it's the span of the columns. But we do want to keep this interpretation in mind as well, that it is the right-hand sides, so that the system has a solution. That comes in handy, but a better way of thinking of it is the span of the columns, and note that guarantees that the column space is indeed a subspace. Note it lives in Rn for n by m matrices. So it's worth explicitly verifying that the null space is also a subspace. We don't have an immediate explanation for that other than directly doing it, so let's do it. Obviously, multiplying your matrix by the 0 vector gets you 0, so we're in the null space. If you're in the null space and you got a scalar, well, multiplying the scaled vector, we know we could pull the scalar out of the matrix multiplication, and then you're scaling the 0 vector, and it's equal to 0. So we're in the null space. And likewise, if we have two elements that are in the null space, then multiplying by the matrix A gives me this summation. Each one of these is 0, and there you go. Multiplying x plus y times A gets me something that's still in the null space. So the null space is the 0 vector. You cannot scale your way out of the set, and you cannot add your way out. Thus, it's a subspace. Nice. All right, and in fact, the column space and the null space are two of the fundamental subspaces associated with a matrix. At some point later on, we're going to get a full rundown of the 4 fundamental subspaces, and I will make a completely inappropriate analogy to the big 4 of thrash metal when we get there. It lines up like really well. Let me tell you, for the heavy metal enthusiasts, it's going to be great. We'll talk more about that later when we get the other fundamental subspaces. But in the meantime, now that we have column space and null space, we actually can quickly establish certain things are subspaces without having to do any work, because you just recognize that what you're working with is a column space or a null space. So for example, let's say I have the following collection of elements of R4, where I know that A minus 2B is equal to 4C, and 2A is equal to C plus 3D. Another way of reading that is that the first element minus the first entry minus twice the second entry gives me 4 times the third entry. And twice the first entry is the third entry plus 3 times the fourth entry. Now, not immediately clear that this is a subspace, but if we set up an appropriately sized and defined matrix, note A, -1, -4, no D, and note the negative because it's on the other side of the equal sign, 2A, no B, -C, -3D, well then if I take A and multiply it by the vector x, y, z, I get the expression x minus 2y minus 4z, note minus 4c over it's equal to 0, 2x minus z minus 3w, note subtract the c and 3d over, it's equal to 0. So, wouldn't you know it, w here is precisely the null space of my matrix A, and there you go, W is a subspace. Has to be. It's a null space of a matrix. Done. That easy. So while you can verify things are subspaces directly from the definition by verifying the 3 axioms that they need to satisfy, here we see that if you actually want to verify something as a subspace, you actually can be pretty clever about it. Just build the appropriately sized, appropriately defined matrix, and life's good. And for another example, let's say I had the collection of vectors in R4 where the first entry is 2s plus 3t, where s and t are real. The second entry is r plus s minus 2t, where those letters r, s, and t are real. And likewise, the third entry is 4r plus s, and the fourth entry is 4r minus s minus t. Well, hopefully you see where this is going. Pretty similar to what we did last time. Set up an appropriately defined matrix with the scalars in the correct spot. I don't see an R, I see an S, I see 2S, I see 3T. There's the first row. 1R, 1S, negative 2T. 4R, 1S, no T. 3R, minus S, minus T. And indeed, if you're to multiply A by a element of R3, you'll get precisely the equations you see here. And I'm using different symbols here to sort of represent, right? The R, S, and T are dummy variables. It really doesn't matter what they are, and whatever you multiply by, doesn't exactly matter. But here we see that anything that looks like this looks like A times a element of R3, so what you have here is indeed the column space of our matrix, so W must be a subspace. No effort, just build the right matrix and you're good to go. Nice. And perhaps you'll be kindly asked to repeat this task in some homework and problem lists. All right, and as promised, we're going to wrap today up by revisiting linear transforms, and we'll kind of see, as we saw before, linear transforms corresponded to matrices, and now we just discovered matrices have column spaces and null spaces, and we'll see that for abstract linear transforms, there's an analogous thing you can do. So a mapping between two vector spaces is linear if it does what we want linear things to do, which is respect scaling and adding. Now, the null space for a matrix, recall, was the set of things so that A times X was equal to 0. And the column space were the things so that B was equal to an A times X. And we can carry this over to our linear mappings between general vector spaces. But now, instead of null space, we say kernel, and we write ker T. Pretty cool. Right, no, set of X so that T of X is equal to 0 in this case. Now here the codomain of T is W, so the 0 that I'm talking about is the 0 element of the vector space W. And likewise, the range of our mapping is the collection of vectors B, so that B hits a T of X for some X. Right, so it's the right-hand side of an AX equals B. Only now AX is being abstractly represented by T of X. So obviously, when we're dealing with finite dimensional things, when V and W are our usual Euclidean spaces, we've got a matrix, and then you can talk about the null space and the column space of that matrix. But for abstract things, we can get pretty wild. So for a classic example, let V be the differentiable functions and W be the functions. We recall from our calculus days that differentiation is linear. The derivative of a scaled function is the scaled derivative. The derivative of a sum is the sum of the derivatives. So what is the kernel then of this mapping? So what are the functions so the derivative is 0? Well, we know that means you have to be a constant function. So the kernel of this mapping is the collection of all scalar multiples of the constant function 1. So it's the span of that set. Oh, look at that. Hey, pretty cool. Pretty cool. All right. Neat-o. Real neato. All right. So that gave us a little sampling and a little flavor of abstract linear mappings. We'll dig into them a little bit more as we go on, but for now, we've seen them, and we've got now fundamental subspaces of the null space and the column space. We saw how we can use those to create and identify subspaces, and we've seen that we can abstractify them just as we've been doing so far here in the vector space era of the course. All right, so that's it for today. I'll see you in the next video.